we define the two-body problem as relative motion two-body problem as R double dot plus mu over R is equal to okay. The solution was R is equal to a square over mu divided by 1 plus e cosine. This is the now if you look at what, this is a good time to visit or just recall what Kepler's laws are. What is Kepler's first law? What does Kepler's first law say?
Body makes orbital.
So Kepler's first law kind of precisely says that he was trying to study the motion of planets. So what he stated was planets move around the sun in ellipses. Okay?
Planets move around the sun in what?
In ellipses, in an elliptical orbit. Okay? So this is the statement here. The planet, namely that the planets follow elliptical paths around the sun. Now what you see is Kepler did this observation and he came up with this first law. If you observe this orbit equation, it turns out this is also the equation of a conic section. You know what a conic section is?
Yes.
What is a conic section?
A conic section.
Yeah, a conic section.
You split a cone into different parts. You can get like a circle, a hyperbola, an ellipse.
Right. So this is a conic section. What this is also
Conic circle.
equation of.
Like a conic section.
Why do we say conic section or conic section?
If you take two cones and line them up, point, that's how you get those.
We have this. We have a cone, inverted cone. Okay. If you section it this way, it's a circle. You know what sectioning is? You know what a sectioning is, right? Sectioning is just slicing it through. So if you slice it parallel to the surface, what are you going to see on the top is a circle. Okay. If you section it like this, it will be an ellipse. Okay. If you section it like this will be a parabola.
What's going on with the ellipse one? Is that supposed to be down the middle?
It's not middle, it's slanted. It's not parallel to the surface. So this will be, if you section just one and if you look at it from here, this will be a parabola. And if you section it like this, vertical, it could be a hyperbola. So what you see is, this is an equation of a conic section. So if you exactly write the equation of a conic section, it is H is P over 1 plus E cosine E. You compare this and you compare this, So this P can be thought of as h square over mu. For a conic section, this P is, for a given conic section, this P is constant. This E is constant. It's only a function of this theta. Right? And it turns out that the solution is also exactly the same. What it means is, see, we did not do any observation to get here. If you look at how we got here, we used Newton's fundamental laws. We used Newton's law of universal gravitation, Newton's second law. We derived this and we did some operations on this to come to this solution. It turns out that this actually encompasses Kepler's first law. You see how powerful mathematics is? You have to appreciate how powerful Newton's laws are and how powerful mathematics is. See, Kepler, you can think about Kepler making observations as hundreds of years of development. Okay, so if you he came to that conclusion after many people told things, and finally he actually interpreted the observations made by one Mr. Tycho Brahe, and he came to that statement that Kepler's that the planets follow elliptical paths around the sun. So if you look at this clearly says these planets or orbits are not just elliptical, they can be any conic section, right? They can be elliptical, they can be circular, they can be hyperbola, or they can be parabola. So these planets can orbit in any of these conic shapes. Okay, and that's what you're going to see. That orbits. What is a? Can you think about a circular orbit? Most planets are actually in circular orbit. Earth is almost in a circular orbit. Okay, you can launch something in a circular orbit. You can launch something. Anything geostationary has to be in a circular orbit. Elliptical orbit, yes.
So when you say a parabolic orbit, does that mean it doesn't stay in orbit and shoots off?
So we'll discuss specifically what these orbits mean. If you're thinking about parabolic orbit, what is the shape of a parabola? Like this way, right?
Yes.
Yes.
So what happens in a parabolic orbit is it reaches a stage where the relative motion ceases to exist. The relative motion in the sense your central body will be somewhere here, okay? And this is an open orbit. It's like this, the orbiting body is here. It's trying to catch up with the central body. The central body is moved. The relative motion between these two ceases. This would be a parabolic orbit. So it will once you launch something in a parabolic orbit, it is just the velocity or the energy is just enough to escape the gravitational pull of the central body, and then it will stay. It's this is a lost in space problem. Okay. If you're talking about hyperbolic orbits, when you do a flyby, you've heard about flyby or slingshots.
Yeah.
So slingshots happen in a hyperbolic orbit. There is enough energy to escape and keep going. Escape the gravitational pull and still keep going beyond this point. In a parabolic orbit, there is enough energy only to escape, but it cannot keep going. It will escape and the energy is all consumed.
So it's, in a sense, it's just going to stop.
The relative motion is going to cease. It's trying to follow this, but this is also moving. The energy is just enough to keep it stationary with respect to this.
Okay.
It's not in the gravitational pull of this anymore. Parabolic orbits and hyperbolic orbits, they are kind of escaped this thing. So it's this whole thing is rotating. Okay? But the relative motion between these two stops. Okay? So what does Kepler's second law say? So now Kepler's laws become very important actually. Okay? So Kepler's second law says, do you remember Kepler's second law? Is everybody clear with Kepler's first law?
Yeah.
Kepler's first law, clear? So read this and tell me if this makes sense. Planets follow elliptical paths around the sun. Clear? The paths of planets around sun are elliptical. That's what Kepler's first law says. And this proves that. Okay? This is actually the equation of a conic section. It just means that Kepler's law is just a special case of this. Okay? So Kepler's second law says, I will take you to the actual law itself. Yeah. So if you look at this, so Kepler's second law says equal areas are swept out in equal times. Okay. Again, you should try to make sense of this, what it means. And the visual depiction is this.
What does it mean, swept out?
Swept out. So it says equal, let's be right, equal areas are swept out in equal time. So it means dA by dt is equal to 0. Okay. So what it means is, look at this figure. This is the central body, right? This is the orbit anti-clockwise or clockwise? How do you make out whether the orbit is clockwise or anti-clockwise? Why is it anti-clockwise?
You see it going around.
Right, that is also an indication. You see this, the velocity direction is this R. H will also tell you the direction, always. So if H is this way, then it is anti-clockwise. So here, you have to understand it in a different sense. What is a prograde orbit and what is a retrograde orbit? What is a prograde orbit? Take a guess.
Of what orbit?
Prograde, yeah. And a retrograde orbit, it's in the same direction. So Earth is rotating in a particular direction, right? If you're orbiting in the same direction, it's a prograde orbit. And that is actually anti-clockwise. And a retrograde orbit is if you're trying to orbit the other way. So our assumption in most cases is, or we discuss prograde orbits in general. It's not that we don't launch anything in a retrograde. The life of a retrograde orbit is much lower compared to a prograde orbit.
Also, what about this thing that's actually orbiting? Does it matter which way it is spinning?
Yeah, that is actually,
that doesn't matter.
it's actually sometimes spinning, sometimes it's not spinning. But the mass itself is so less that its spinning doesn't have a lot of effect on its linear motion. Okay? Although you can impact the linear motion by its attitude. You know what attitude is? Spacecraft attitude. You understand that? Aircraft attitude. Orientation. Orientation is very important, right? If you, for a linear motion, if your rocket has to go up, what has to be its orientation? Has to be like this. The thrust has to be opposite that. Whatever it is facing, if it is facing this way, that is its orientation, right? So if for a spacecraft also, that orientation matters. When it is in orbit, if you want to change an orbit, how do you change an orbit? You orient your this thing, spacecraft, and then you fire with thruster so that it goes. That orientation matters. So what it says here is, this is a retrograde orbit, this is a prograde orbit, it's moving in this direction. If you are looking at an elliptical orbit, okay, the central body is always, you have to understand this for any orbit, the central body is at the focus of the conic section. You understand what the focus of a conic section is? What is the focus of a conic section? It is not the center of the conic section, always.
It's where the sections revolve around.
In this example, would it be like where M1 is?
Huh?
In this example, would it be where M1 is?
Where M1 is, right. So for elliptical orbits in particular, what happens is, so this is your elliptical orbit, okay? The way you draw an ellipse is, you have these foci, okay, F and let's say F star or F prime. A foci, what you do is, you take two pegs, insert it here. That is how you draw an ellipse. And you tie a piece of thread around it, string around it, and then you stretch it to draw an ellipse. So these are the foci. Okay? You cannot draw an ellipse from the center. Now the central body is always at one of the foci. It is never at the, only for a circle you can say it is at the center, because the focus and the center for a circle is the same. You get it? Make sense? Everybody?
You call those forces?
Foci.
Okay.
One of them, F, is a focus. Okay? F and F star, it's a plural of focuses. Foci or foci. Got it?
What do you say about center?
The center, where is the center of this? The center is where the major axis and the minor axis intersect, right? This is the center. The center and the focus is not at the same point for an ellipse. However, the center and focus is the same for a circle. Alright? Make sense?
But on the left center, it goes to the larger body, or
The larger body is here. So when I say larger body, instead of larger body, I say central body. the central body is at the focus, is at the one of the focus. It's never at the center except for
So,
circle. Make sense? Everybody? So what happens, why is this important in the context of this? Okay. Now you think about this. Just think about this area and think about this area. Okay. So this is the area of a sector, right? The time taken. So let's assume for a minute that this area is equal to this area. Okay. The time taken for the body to go from, for the orbiting body to go from here to here is the same as time taken from here to here. You see that this distance is bigger than this distance. Okay? What it means is, see, this is much smaller, right? It will travel much faster when it is closer to Earth because it has to cover more area. This is the area it is covering, it is sweeping. When it does that, it is sweeping areas, right? dA by dt. You understand? It is sweeping area. So this is it's the same. You take any section, the farther it is, the slower it goes. Got it?
I understand that, but what would cause a central body to have an elliptical orbit? Why wouldn't it pull on the orbiting body staying all the way around?
Not good.
What would cause the central body to have a different pull around the orbit? Why wouldn't it pull on the orbiting body the same all the way around?
There are two forces which will define what orbit. One is the gravitational force, which is attracting, and the velocity at which you launch something.
Okay.
So how do you launch something? You go up like this, and then you do that. Have you seen a launch anytime?
Yes.
If you go up like this, when you launch it, it depends on it. It's a function of we'll take a look at how these orbits are a function of position and velocity. Okay. But when you launch something, based on what velocity you launch, so if you launch it here, right? If you do this and you start going this way, if your velocity is higher in this, then you may form an elliptical orbit. If you want to go to a very highly elliptical orbit, you know what a highly elliptical orbit is? So it is, when it is closer, it is really, really close. When it is farther away, it is really far. Okay? So you can command it when it is closer. If you want to, let's say, go to very close to the moon, right? But at the same time, you don't want to. You want to command it, or you don't want it to do a huge orbit, like a circular round moon. So what are you going to do? You're going to launch it in a very highly elliptical orbit,
Okay.
where it is very close when it comes to where you can command it, ask it to do certain things, and it will then go very close to moon and do its job and come back. We'll take a look at how these orbits are formed. But the basis is this. This defines the basis that an orbit can be any conic section. Okay? How we can achieve those orbits, we'll discuss this. Alright, so this is Kepler's second law. Okay? Yes?
So you said that area, we
move faster because it's closer to the central body?
Hmm?
You said this area, the smaller, will move faster because it's closer to our central body.
It's based on this law, so I don't think this is
I don't
true.
understand that, but
It's sweeping, right? So
I don't
you're
know what that means.
so think about this. You're taking you have this, okay?
Oh,
It's sweeping. It is sweeping areas. When it is moving, it is if you connect something. This is the central body, and the orbiting body is, let's say, here, here, here. It's moving like this, right? It's moving in an ellipse. When it's moving, it's sweeping areas. If you do this, to sweep areas. Sweeping is it just means it is covering area. Yes. So it is just covering areas. So what it means is the area covered per unit time is always the same. And that for an elliptical orbit, because that has to be same. See, what is the area of this versus this? How would you calculate the area of this? Hmm?
How do you calculate the area of that?
Mm-hmm.
Based
R theta will give you
the
this one, right?
Yeah.
And if you just do a half R theta into this R, you'll get the area, considering this as a triangle, right? Area, if you consider this as a triangle, you'll do half base into height, right? So this, if you see that the function is, the area is only a function of the R, right? So here R is much smaller, but here R is much bigger, right? So to compensate, this will be much bigger. This will be much smaller, right? Because that area has to be the same.
Would you say that it's going like a slingshot maneuver, or does the gravity of the M1 have nothing to do with propelling it forward?
The gravity, see, there are the velocity direction. If I show you here, it is like this. Okay. So what is happening is there is a component of velocity which is tangential to this, which is perpendicular to this. There is a component of velocity which is radial. Okay. This component, the radial component, you understand what a radial component is? Along the radius, right? That component is required to keep it from going out, because this component is required to keep it from coming down. Actually,
The
gravitational attraction is there, right?
the radial is designed for that?
Right.
Yeah.
It's not designed. It's that way. The radial component will make sure it doesn't fall in. Okay. This component will make sure it is always in that conic section.
Which component?
The tangential component.
So if it was slingshotting around, like it wouldn't have a good radial component because it would slingshot the wall.
Right. It will have a very huge radial component actually. So it will just, if you try to tie a string and you try to rotate that, you'll feel these two components. You actually can feel the components. Take a heavy heavy mass, tie it to the end of a string and just rotate it. You'll feel that there is a component which is trying to, the centrifugal force or the centripetal force, this what is trying to push it away. Okay. So this is Kepler's second law. Everybody is clear with Kepler's second law?
Yes.
See, it happens that Kepler's second law, or this is your definition of angular momentum. Kepler's second law embeds angular momentum in it. Okay. Finally, I'll talk about how it does that. Let's talk about Kepler's third law. What does Kepler's third law say?
Let's see.
Anybody? So Kepler's third law says, defines a relationship between the time period of an orbit and the average distance. Okay, the square of the time period is proportional to cube of the distance from the center. So what does that mean? The farther it is, the orbit period. You know what time period is? Orbital time period. What is orbital time period? How much time it takes to orbit once, to complete one orbit. So the farther it is, the more time it is going to take to orbit. Okay? Huh? Right. So this, you can say, I can do this as well, r cube. R cube is what? The distance. R is the distance from the center. But this r doesn't remain the same for an ellipse, right? This r is constantly changing. So what do? We take the average r. You understand?
Yes. Can you verbally explain that relationship again? You said the times.
I'll pull up the Alright, here's Kepler's third law. So what you see here is Kepler's third law given as an equation, a mathematical expression. Okay? The actual definition is the period of a planet is proportional to 3/2 power of its semi-major axis. Okay, that's what I had written earlier. A is not the area, A is the semi-major axis. What is a semi-major axis? Huh?
The largest axis of the cross.
Semi-major axis. What is semi-major axis?
So the half of the major axis,
Half of the major axis. What is a major axis?
the longest end.
Yeah, this. So this,
You said
that is the minor axis. Okay.
What's the minor axis?
The minor axis is this. Semi-minor is this. Major axis is this. Semi-major axis is this distance. Semi-major.
you said the A is not what?
A is the semi-major axis. It's not area. So you should try to understand this relationship. P square is proportional to, it actually says the same thing over there as well. So what is it written over there? P is equal to 2 pi over root of mu, right? A 3 over 2. So this and this are the same. You realize that? This is a constant, right? 2 pi is constant, 2 is constant, mu is constant. So what we have done is, we have just replaced this proportionality sign with a constant. And if you take square root on both sides, the left hand side you are going to get t, the right hand side you are going to get a 3 over 2.
So, a constant is called that's just for this one.
You can derive that constant. You can figure out that constant. But what you need to understand is this. This is what you need to remember. Okay. So here are Kepler's first law, second law, third law. One, you have to remember the laws, the statement of laws, and you have to understand what is the mathematical significance of it. Okay. So now we can mix this off for a while. So everybody is clear with the laws?
So,
Yes, Raju?
the T was for time period, right?
Time period, yes.
I have a question, Dr. Sunny. Why is the capital T instead of lowercase t?
It's just a notation, it doesn't mean. See, generally time is, what is the difference between time period and t? What is the difference between this t and this t?
That big T is constant.
It's actually a constant.
Okay.
This is generally used for a constant, this is a time variable. Okay? If you differentiate this t, what are you going to get?
0, 0.
If you differentiate that t, what are you going to get? With respect to time,
T is one.
it's 1. Okay? So this is a general notation, it's got nothing to do. Just a practice. Okay?
You're saying A is the average.
A is the semi-major axis. See, it turns out, if you, this semi-major axis, what is it for a circle?
Radius.
It's the radius, right? It turns out, if you take the average of the, here what is the radius, the so-called radius? Is this distance, right? You understand that? If you average, so this, when it is this, the point of closest approach, you understand what the point of closest approach means? This is the point of closest approach. That is when the orbiting body is the closest to the central body. That is generally called the periapsis. We will discuss those points. The point of farthest approach is called apoapsis. Okay? If you take this radius and average it, the radial distance, if you average it, it turns out to be the semi-major axis.
That's good work.
The semi-major axis. It's equal to the semi-major axis. So that is what we are saying here. This is the average radius. A just means it's the average radius. It can apply for ellipse, it can apply for circle, it can apply for any other. So what is it for parabola? What is the semi-major axis for a parabola?
Say again?
What is the semi-major axis for a parabola? How do you define the semi-major axis?
The vertex.
Huh?
The vertex. The vertex.
How much is it? What is the semi-major axis of a parabola?
Does it have one?
Huh?
Does it have one?
It doesn't have one. It has one, but it is actually infinite.
Okay.
So what is the time period of a parabolic orbit? It's infinite, right? Because it has to be really big. It just stays there, right? It never comes. So. So you have looked at the different Kepler's laws. You have to keep in mind the orbit equation. It's very, very important. Okay.
Represent.
Yes.
So, for you said for a parabola that stays there, is there a possibility that the gravitational force is strong enough so that right before it gets to that point, it comes back? So it's like a pendulum kind of.
Say that again.
Is there a possibility for the gravitational force to be a certain strength so that when it almost gets to that point, it like comes back like a pendulum? Like an object? No.
See, unless the gravitational force is a function of time, that's not going to happen. The gravitational force, as we understand today, it's constant. It's practically constant. Although, if you look at what happens to a gravitational force for the sun, will ultimately become, let's say, a black hole, right? So the gravitational potential or the gravitational force changes, right? But it changes over a really, really long period of time. So if you think about that period as becoming shorter, then something like that, like what you told may happen. But for practical this thing, it's a constant. It changes over millions or even billions of years. Just you have M1 here, okay? And M2. Okay, we'll define a few terms here. So this is M1, here you have M2. There's something called apse line. What is apse line? Apse line is just the line joining the periapsis and apoapsis.
Line joining what?
Periapsis and apoapsis. What is periapsis?
So the smallest, shortest distance between the
It's not the short, it's not a distance, it is a point. It's the point of closest approach. It is a point when the orbiting body is closest to the central body. Okay. What is apoapsis? Again, point of farthest approach. And apse line is simply the line joining these 2 points. Got it?
Say it again.
Apse line, this apse line is simply the line joining these 2 points. Okay. These apoapsis and periapsis are terms used for any 2 central bodies without regard to what the central body is. If the central body is Earth, this periapsis can also be called perigee or perigee. You've heard about perigee a lot of times. You've not heard about perigee or apogee? Right, so perigee and apogee are specific to Earth. That G is from geo. Okay, the geo means Earth, right? So this periapsis becomes perigee. Apoapsis becomes apogee, right? If Sun is a central body, then this periapsis becomes perihelion. Okay. If its apoapsis becomes apohelion, because the central body is Sun. All right. Now this distance. So what we do is we define this direction. This E is that direction. The line joining the center or the central body and the periapsis. We define this. What is this vector? Do you remember this vector E? What is this vector E? How did we define this vector E? You remember we defined, when we were deriving, we came across this C vector. Right? What would we call that C vector? C vector was the Laplace vector. Okay? And C over mu we defined as E. Okay? And it is simply called the eccentricity vector. It defines a direction. Yes.
Did you just take the periapsis and the apoapsis and put them in the same direction? Like the same, so that they were wrapped in the same plane? Like, well, not the same plane, but the same direction, I guess.
Can they be in the same direction?
No, I'm saying, like, the periapsis would be the closest point,
Mm-hmm.
and apo would be the farthest. So would you like take those and put it so that they're in the same direction for the apse line?
Apse line is just a line joining those 2. So this is the apoapsis, right? This is the periapsis. This line is the apse line. This is that line. That line is going to pass through the center. Got it? That is that apse line. Okay. E is the eccentricity direction or Laplace vector direction.
So you said it's passing through the center of the body, right?
It has to pass, not the center of the body. It passes through the central body, which means it passes through the center of the body. Yes.
Okay.
There are 2 bodies. Remember, there are 2 bodies. M1 and M2, right? We are always talking about 2 body problem. One body is practically fixed. This M1 is fixed. For all practical purposes, this M1 is fixed. See, we are talking about relative motion. You understand why we are talking about relative motion? We are talking about relative motion of M2 with respect to M1. Right? So in that sense, that M1 is fixed.
So if the epsilon passes through the center of that fixed body, how's the fixed body at the end of the epsilon?
Huh?
How's the fixed body at the end of the epsilon instead of somewhere on the
It's
line?
not at the end. So this is, it's just passing through that line.
So there is no whole other side to that, so that.
There is, you can do that. So this is apps line. This entire thing is apps line. Apps line is from this point to this point. It will always pass through the center. Or it will always pass through the central body. You got it, Clayton? So this line is actually, you can extend it as well. It will not change. The definition will not change. Okay? So now you understand what this E direction is, how you define this E direction.
You said the E was the Laplace what vector?
C is the Laplace vector. C over mu, which is E, is the eccentricity vector. You know what eccentricity is? What is eccentricity for a conic section? Alright, we'll discuss that later. So just for now, just understand that C is Laplace vector. E is eccentricity vector. Okay. Now, what is important here is there are two components. See, your velocity is, this is the velocity of M2. Okay, that R dot is the velocity of M2. Now this velocity will have two components. One is the radial component. Do you see the radial component?
Yes.
This is the radial component. Okay, and this is the tangential component. That makes sense?
Yes.
Okay. How do you define H? What is the definition of H? What is an expression for H? H is defined as R cross B, right?
Is that, where's H on there? Or are you not present?
This is H. That you have to always know. Just looking at this, you should know where H is. Because R is this, always right hand rule, R cross MV. R cross V has to come this way. See your velocity direction, I have shown you where the velocity direction. You know where R is, H has to be. See, none of it is there. H is not there, V is not there. If you just physically see it, what does it? Something orbiting something, right? So this is all mathematically you are making sense of what it is. If you understand where H is?
Yeah.
H is coming out of the board. Okay? This will always be the case. Even in this, where is H? It's coming out of the board, right? So because this thing was anti-clockwise or prograde orbit, it is coming out of the board. Right? You see R cross V. R, V.
Where's it? Say it one more time.
R cross V. R is this. V is this, right? You do a R cross V here. It has to be this. So this would be your R, right? You see R cross V. Or R, V, R cross V. You can do that as well. Okay. Your R is this. If you keep, this is that R.
What is that? I was just-
So this is R, right? Got it? all of these have to be at a certain point. You either take this point or you take this point. If you take this point where your R is this direction, your V is this direction. Now your H is this. Got it? You have to move it at a certain point and then figure out. So your H is equal to R cross V. Now what you are going to see is this radial component does not contribute to the H. Okay? Why does radial component not contribute to? So this is what you can say. This R crossed with V plus R crossed with VR. This is 0. Okay? You understand why that is the case? And this is no. Why you don't understand why that is the case? Tell me why that is the case.
In the same direction.
They are in the same direction. If they are in the same direction, what happens? The cross product is the sine of angle between those two, right? So it is that angle is 0. Okay? So it is only, it happens that it turns out that this H is only due to the tangential component of the velocity. So you can say V prime, V this thing. You can express this V as R theta dot, okay, implying H is R square
Are these all vectors?
Hmm?
Are these not vectors?
These are not vectors. We are talking about the radial component and this direction is known. Okay. This direction is always tangential. Okay. Why is it R theta dot? What is R theta?
R theta is at the circle.
It's this thing, right? R theta will give you this. R theta dot is simply change in the, it actually gives you that radial component. Okay. Theta dot is angular rate, and if you multiply that by R, you're going to get the linear velocity, that is this. And this is just the magnitude of that. Okay. So if you substitute this here, okay, you're going to end up with r square theta dot.
But didn't like they are a cross product, so.
Yes, so here we are concerned with the magnitude of this. The direction is always this. Okay. You can simply put this and say this is perpendicular to R and B. Okay. And we are going to use these formulas at a later stage. That's the reason I want you to understand this. So this is the magnitude of angular momentum. So this is B perpendicular to H over R. Right. How do we get this? Hmm?
H squared over mu divided to 1.
So what you can do is
Just reciprocals.
so recall this R is equal to E square over mu into 1 plus E cosine theta. Okay. So if you substitute
Into the, yeah.
into this, you're going to end up with this. Okay, so you can see that you just put R here, this H cancels with this H, mu will go up and 1 plus E cosine theta remains there. Okay. Similarly, you can get an expression for VR, U over H, V sine theta.
What is the expression for VR?
So VR is what? It is simply R dot. You agree?
VR is R dot.
It's R dot, which is d over dt of a square over mu into 1 plus e cosine theta, right? So this would be a square over mu over 1 plus e cosine theta square, right? And minus 1 plus e minus sine theta. So this becomes got it? There will also be a theta dot.
So you just did the substitution. You just
No, I took the derivative first. So what is the derivative of this? Is derivative of 1 over r. Think about it as derivative of 1 over something. It is minus 1 that thing over this thing square, right? Make sense? And then you have to take the, because this is a function of, you have to do the chain rule. It is e, 1 is 0, then you have e sine theta, which is negative. Negative, negative, this becomes positive. Then you have a theta dot. Okay? Now just look at this. You can see that if you, what is h? H is r square theta, right? If you look at this, okay, you can write this as h square over mu 1 plus e cosine theta. What is this? This thing is simply R. Do you see a R here? R over 1 plus E cosine theta. You see that?
Actually, our times 1 plus equals.
Huh?
Yeah, our times equals 1. Our times 1 plus equals 1. That equals x squared.
No, it'd be divided.
But R is equal to that. And then you have it squared in the numerator. Well, so you
Yeah,
have
it would be like our times 1 plus equals 1.
Why is it R times 1 plus E cosine theta? So actually R over 1 plus E cosine theta.
1 plus E cosine theta?
Yeah.
From like up there,
No, that's
R equals
There's a 1 plus E cosine theta squared.
yeah.
So there's 2 of them.
There are two. If you remove just one, this is R, right? A square over mu 1 plus E. That is, so that 1 plus E cosine theta remains there. Okay? And then you just keep this E sine theta into theta dot. Okay? So what do we need now? You need, instead of, this will remain as it is, instead of this you need a mu over H. How do you get mu over H?
Maybe.
Mhm.
Oh.
So we need new over H instead of what?
So what we need is, you think about this. R
Oh, you can do, I think, that R equals x over v1 and then x over v.
So think about this, okay? You have
So,
H is equal to R square theta dot, right?
you can substitute that, hit that dot with v1 over r. Oh, sorry.
Right. So what you can do is, you can do this is equal to R over 1 plus E cosine theta. So theta dot is R square over H. Okay? And
Dot is H over R squared.
theta dot is H over R square.
Well, that's what R squared.
Okay.
H over R square
No,
E sine theta.
it's easy to substitute v1 over r.
Hmm?
It's easy to substitute v1 over r at the place of theta.
This is, you have R is 1 plus E cosine theta over 1 plus E cosine theta plus E square over mu H E sine theta. And this mu goes, this is equal to, this cancels. So you have mu over H E So what I did is, I just substitute for theta dot. Theta dot is what? H over r square. We cancelled square and r here. Substituted for r. R is what? H square over mu into 1 plus e cosine theta. 1 plus e cosine theta, 1 plus e cosine theta cancels out. H square cancels with 1h. There is 1h in the denominator. Mu goes into the numerator, then the e cosine theta remains.
What I did was like theta dot equals d1 over r and substitute d1 with mu over h, 1 plus equals theta and
So you can do that.
Why doesn't, H is specific to your momentum, right?
Mm-hmm.
Okay.
It's also very the opposite.
Right, this is important. I just proved this to you. How we got it. You have to remember these.
Because you got I'm actually about to go meet with Dr. Alfred now. So